Hello, and welcome back to the last unit in this major module looking at the complete synthesizable subset of the Verilog language. Here what we're going to look at are common problems and fixes that you will see in your code, functions and tasks, which we'll illustrate using a linear feedback shift register, and arrays, which we'll illustrate the use of via a register file before finishing off with a substantial example in which we'll design a modest module from specification through to Verilog. A very important part of this particular unit are the common problems and fixes. You will see these problems in your design as you progress through larger and larger examples in this class. And you need to know why they are problems, because sometimes that might not be apparent. How do you detect that problems have occurred, and how do you fix them? In addition, functions and tasks and arrays are useful and sub-elements that are synthesizable, and it's valuable for you to know how they work. Here are the references for this particular section. So let's start. When you start designing somewhat more complex modules, this will most surely occur fairly early in your design career. It certainly occurred early in mine, and that is unintentional latches. The problem here is, if you look at the code on the left, we're trying to model some combinational logic. We're trying to model the behavior of that combinational logic. But what happens to C if A is low? C does not change. That is, C is stored in a memory. There's only two types of memories, latches and flip-flops, so C is stored in a latch. Similarly, if A is high, D is stored in a memory, i.e. a latch. And the problem with this is that though your RTL simulation might show no problems, in the actual hardware you'll have problems galore. And the reason is, this latch is not fed by this nice pure clock distributed on the clock tree. What's the clock input to these latches here? It's A. And A is coming from another piece of combinational logic, and it might be glitchy. That is, during the clock period, A might change several times. Each time it changes leads to a latching event, and if the inputs change during that time, you'll get metastability and setup and hold problems. This will lead to actual transient failures in the design. Unfortunately, at the RTL stage, the code is timing unaware. The only timing you have at the RTL stage is some specification for the clock period. You don't model setup and hold. You don't model actual delays in logic. You won't see glitches, you won't see metastability, even if they will occur in the actual hardware. So you might ask, how do you detect that this is happening if you won't see it as a problem in the pre-synthesis simulation? Well, fortunately, synthesis has parsers that look for problems like this. In particular, in Synopsys, after the read command, you will see a list of flip-flops and latches. And frankly, for the purposes of this class, if you have any latches, you've got problems, because that means they are unintentional. How do you fix this? Well, it really depends on your logical attempt, what your logical intent was. So I can only illustrate how to fix that. But what you have to do in general is make sure that all the outputs of the combinational logic are assigned for every possible way in which the procedural block is executed. One way to do that is to use defaults. Here what I've done is pre-defaulted C and D to don't care, assuming that's my logical intent. This way C and D are assigned every time this block is executed. That means there's no memorization of C and D between executions of this block, and we don't have any latches. Of course, in the actual synthesis, C and D will be optimized out. You won't, of course, don't have don't care values in the actual logic. The next one we'll look at is an incomplete sensitivity list. Admittedly, this problem is specific to verilog25, so you really only encounter it if you have to deal with legacy code. But it's quite likely you'll have to deal with legacy code, so I want you to be aware of this problem. Look at the logic on the left here. Does this logic get triggered if D changes? No, it doesn't. So D is a logical input to this combinational logic block, but this simulation won't behave correctly if D changes. Thus, you have a bug in the design. You may or may not exercise this bug during pre-synthesis simulation. It doesn't mean it's not there. If you don't exercise it, it's just you didn't exercise it. It takes a lot of simulation to exercise all the bugs in your design. We'll talk about verification later. So again, you might not detect this in simulation. Simulation is unaware of whether you're intending to model actual logic or just writing general code that just happens to be in Verilog. Here again, we rely on the synthesis tool to tell us that we've got a problem. In Synopsys, again, this is after the read command, it'll tell you with HDL warnings that you have incomplete timing specification lists, which mean you have to go back and fix them. How do you fix this? Well, if you're coding from scratch or even recoding a design, you can always use the verilog2001, always at star. Or if you have to stick to the verilog95 language, you have to complete the sensitivity list. But here you might be asking, wait a minute, doesn't C have to be in the sensitivity list? It's on the right-hand side here. And the point is, though there's no harm in putting C in the sensitivity list, it doesn't technically need to be there because C is an internally produced signal. Thus, you won't be getting incorrect behavior because it's not an input to the actual logic block that this is actually modeling. Next one I'm going to look at is what I call unintentional wired OR logic. This is very common when people write a lot of code without doing design beforehand. Because in normal code, it's quite fine to assign a variable many times in many different places as it changes during the execution of the code. That's not how hardware works. For example, look at this code on the left here. C is assigned in 2 different blocks. What we're doing is taking the output of an AND gate and shorting that to the output of the OR gate. What happens if one gate is trying to drive C high and the other gate is trying to drive C low? What would actually happen is that one of them will win, but you don't know which one will win. So this is not good logic design. Each signal can only be driven by one procedural block in the entire design or by one continuous assignment statement. So the way to fix this is to really tear up that part of the design, go back and actually design it to work out what the logic blocks are, give unique names to the outputs of each logic block, and code it and capture that in code. So again, here the possible fix I'm presenting is not necessarily a general way to fix this. The best way to fix this is actually to go back and redo the design. But it's plausible here that you intended this to be an output of a mux. You just didn't capture that properly, so a mux might be a good solution if you feel if this signal really is a common signal in your design. Another possible fix you might be asking about is, hey, why not intentionally create a tri-state bus and fix it that way? Because a tri-state bus is the only way in which you can assign a signal multiple times. I remind you that I discourage you from building tri-state buses because you need an arbiter then. And you need to design that arbiter to make sure the bus is only driven by one source per clock cycle. So again, if your intent has a tri-state bus, fine, we'll code it. If you didn't have that in your design, then don't think that by putting one in after the fact will fix all your problems. It's unlikely to do so. Again, you won't detect this in the RTL because the RTL is agnostic as to whether you're modeling synthesizable designs or not. You'll detect this after the read command in synthesis, or specifically in synopsis. It will say variable assigned in more than one block and point to you where that is happening. You have to fix all these HDL warnings in synopsis. You cannot go ahead with the rest of the synthesis run if you have warnings like this or the previous ones in your design. You're just synthesizing garbage. Next one is a little more subtle, and it's more a good methodology practice than something fundamental. And unfortunately, it's something the synthesis tools or no other tools, except possibly some lint tools, which we're not using in this class, will tell you about. But this does reflect a practice that is industrially relevant, so I do want to introduce it to you. I'm calling this potential problem improper startup. And it's really caused by incorrect propagation of don't cares. You see, the way simulation works internally is in Verilog. All signals are initiated to unknown, which is fair enough. The start of simulation, they are unknown. Eventually, the code assigns a logic value to the signal, and you'll see it changing from unknown to some logic value. Well, what can happen, what you want to make sure is in your design that is actually done, that all signals eventually get written with correct values. However, if you design your combinational logic incorrectly, you can accidentally turn a unknown into what looks like a real logic value, and that could hide a bug, particularly a bug in your reset logic. So here we have an example. Let's say we have this flip-flop here, and this actually is part of the state of the machine, and we should have applied reset to it, but we forgot to do so. So there's no if reset bar, q equals 0 or q equals 1. The output Q of this then goes to a combinational logic block. And here we have a case statement. We really only cared about 0, so we said if Q is 0, F equals E, otherwise F equals 1. What we were really thinking was if Q is equal to 1, F will be equal to 1. However, what you've accidentally done is also said if Q is equal to X, F is equal to 1. Thus, you can get the simulation down the bottom here. So again, D was initiated don't care. We forgot to apply reset to Q. So that is don't care or unknowns more precisely. Once at some point E changes, triggering the execution of this block, it executes, Q is equal to X, so it says F equals 1. You've suddenly turned an uninitiated signal, an unknown signal, into a known signal, a logic 1. And if in your RTL simulation you're looking at F and not looking at Q, you will think you've distributed reset correctly, and you'll be hiding a bug in the reset. Unfortunately, it can be very hard to find these. Synthesis does not tell you about them, and here we've illustrated how RTL is masking the problem for you. So what is recommended is that you write all your combinational logic blocks so as to propagate don't cares. So here's an example. I've rewritten this case X statement. If Q equals 0, F equals E. If Q equals 1, F equals 1. Default, which will cover Q equals unknown, F is unknown. What you've done here is if Q is X, the output of this is X, and you're not accidentally hiding a bug in your design. And you're doing this by basically making sure you propagate don't cares through your design until they're properly assigned to a 1 or a 0. I recommend that you use this coding style. I must admit, in this class up to now, I've sometimes used this and sometimes haven't. But frankly, I've got limited space on these slides, and because this point wasn't illustrated yet, I chose sometimes not to do this simply for the purposes of lack of space. But I do encourage you to propagate don't cares using this type of approach in your actual designs. Another very common problem when people don't design before coding is feedback in combinational logic. Again, this might simulate fine. Since there's zero delay in RTL, it'll just look okay. But in real hardware, it's a fault because you don't know the delays of the actual logic. All you know is their min and maxes. So you can get an infinite loop here. When this is sampled into a flip-flop, say that's put here at this point, you don't know what will actually be because you don't know what stage you'll be at going through this infinite loop. Or it means you could have an embedded latch in your design, which is also bad. Again, synthesis tells you about this, not at the read command, but later. It will refer to timing arcs in your design. What that's saying is that you've got a combinational feedback logics path in your design. And this has happened by not sketching out your design before coding it. If you sketched it out properly, knowing you can't do this, then you would not have sketched this, which means when you coded it, you would not have done it. You would not have coded this. So it often really is an example occurs when people don't do a thorough design before coding. If you need some sort of feedback, it has to be through flip-flops. That way, the feedback path only gets exercised once per clock cycle and it's synchronized by the flip-flop. So a logic structure equivalent to this on the right is perfectly fine and is actually very common. Another relatively common but less common structure problem is the incorrect use of for loops. A lot of people really try to skip the design step or don't know how to do the design, a little flustered by it. So they just start writing C code, slapping in always pos edge clock statements. And since in C code a for loop is quite fine to specifying the control of a multi-step event, I think fine, I'll just slap an always at pos edge clock on the front of this. And in the counter we've already illustrated how this will lead to incorrect behavior. And I remind you, going back to a previous unit in this module, the only valid use of a for loop is to iterate through an array of bits. And they can be useful for that, but that's not usually what I use a for loop for in the C code. So you've got to be very careful about when you use a for loop. And if you need more detail on this, go back to the unit that discussed for loops. Another common problem is what's called unconstrained timing. And this is not really a fundamental issue in design, but it's a side effect of how synthesis manages constraints. Synthesis, Synopsys in particular, needs every path from an input port to an output port in a module to go through a flip-flop. If it doesn't know how to calculate the timing for those paths and refer to those paths as unconstrained paths. There's really two ways of fixing this. One way is to go back and constrain the path. For example, you could work out the clock period minus the input delay minus the output delay and say this is the delay required for that path. However, that is very tedious to do that for each and every path in your design that's unconstrained. It is better to properly design your modules so as to include flip-flops in all the paths from the primary inputs to the primary outputs. Really, this means your module should be large enough to cover a reasonable expanse of logic, which is really the way to approach it, and we'll talk about this later in module partitioning. But this is a problem you will see, and you need to fix it by making sure in your modules there are flip-flops between all the primary inputs and all the primary outputs of the module. Another problem you'll see, which is less of a problem if you're at least aware of why it's happening, are unconnected nets and wires. This will be reported to you in the check design step. This is really only an issue if it's your custom created logic that's doing this. Usually this occurs because you're using intellectual property blocks for things like adders, and you've got inputs and outputs that you don't need, or specifically outputs. You want to make sure all your inputs are connected, because otherwise your adder will, or whatever it is, will go into undeterminate states. But really, if your outputs are unconnected from intellectual property blocks, that's not a big deal, and that is fine. So that brings us to debug, which has really got to do with verification, but I do want to talk about it a bit here. Initially, when you start coding, a lot of your bugs will be syntax errors, dropping semicolons, using incorrectly specifying Verilog, and it will take you even a while to learn what these are and how to fix them. For example, if you drop a semicolon, the problem often occur on the next line after the line in which you forgot to terminate with a semicolon. But once you're beyond that, you're really dealing with bugs in your logic. And here the most important skill is to be able to produce a timing diagram for your design by hand and compare it with the timing diagram that the tool is specifying to you. And then tracing back the cause of the mismatches between what you think the timing diagram should be and what the simulation tool is telling you the timing diagram should be. This is tedious, it's hard, it requires focus and concentration, and that's the way it is. You've all done coding, you know what it's like. Right? But as you climb the learning curve, it will become a bit easier. But nonetheless, you have to attack this problem with diligence and discipline. So tracing back problems in the design and in time is important. Here, of course, the Verilog commands, $monitor, and being able to print out status of signals at various times is useful to you, as well as tracing through signals on the waveform generator. And one trick that's actually sometimes useful, if you really get stuck and you cannot work out what is causing a bug, just recode it. Just try something different. By the way, this applies in life as well. Some people get stuck in trying the same old thing again and again and again, particularly in relationships, and will lead to predictable results. If you do something different, then often it's appreciated and solves those real life problems as well. Here it works not because just a different version of the code will suddenly be a correct code. It's more likely to bring your attention to what really causes the problem and allows you to fix it. So remember, if all those fails, try something different. So that brings us to the end of this submodule. Again, summarize the main problems, how they're detected, and how they're repaired. Unintentional latches are reported after the read. You have to remove them. Incomplete sensitivity lists are reported after the read. Complete the list or use star. Wired or logic is reported after the read. This is a design problem. You have not designed before coding. Go and do a design to work out your logical intent. You can only have, every signal can only be assigned from one piece of logic. Improper startup can't be detected, but I encourage you to write your combinational logic code to propagate unknowns. Combinational logic feedback will lead to timing arcs in synthesis. You have to redesign it so that it's again usually a problem of not designing before coding. But if you need feedback, then put it through a flip-flop. Incorrect use of for loops is usually detected in RTL simulation. It's often used when you're really intending control intent to go through a fixed number of steps, and you're using a for loop. The only valid use of a for loop is to iterate through an array of bits. If you want to go through a fixed number of steps, you have to design a counter in order to count those steps. We'll talk about that in a later section. Unconstrained timing will be reported as such in synthesis. This occurs because you don't have a flip-flop between an input and an output of a synthesizable block. You should make your modules large enough so that between all the inputs and all the outputs there are at least one flip-flop so that Synopsys can work out the timing. I now encourage you to do the quiz associated with this submodule before proceeding to the next submodule. Thank you very much.